Hello, welcome to our channel Inventive Education. We are currently learning Newton's laws of motion. In this video, we are going to learn about frictional force.
Now, what is a frictional force? A frictional force is a force that opposes the motion between two objects that are in contact. It acts between two surfaces that are in contact and resists their relative motion. For example, suppose that we have a wooden box and we slide it on a flat surface in the horizontal direction. We will notice that after traveling a certain distance, this box stops, indicating a deceleration in the box. This deceleration indicates that there is a force acting on the box in the direction opposite to the motion of the box. This is the frictional force and it acts between the surfaces which are in contact. In order to keep this box sliding at a constant velocity, we have to continuously apply a force in the direction of motion. This applied force overcomes the frictional force and this box is able to move at a constant velocity. Now suppose that we have a large wooden crate and we try to move it on a flat surface by applying a force in the horizontal direction. But this crate doesn't move. This is due to the frictional force which acts opposite to the direction of the applied force and it acts to prevent the movement of this crate. All the force that is applied on this crate is spent to overcome this frictional force, resulting in a net zero force on this crate, and therefore this crate doesn't start to move. In this first example, the frictional force is applied on a box which is moving. Therefore, this type of friction is called kinetic friction. In the second example, frictional force is applied on a box which is stationary. Therefore, this type of friction is called static friction. Now we will see the kinetic and static friction in detail. Now suppose that we have a flat surface and an object is kept on the flat surface. If we are not trying to move this object, the only force that are acting on this object are the gravitational force and the normal force. Now if we try to move this object with a small horizontal force, frictional force kicks in and prevents this object from moving. If we increase the applied force, frictional force also increases and this object still doesn't move. If we increase the applied force further, it breaks the frictional force and the object starts to accelerate. And if we want to keep this object moving with a constant velocity, we have to reduce the applied force such that it is exactly equal to the frictional force. In these two cases, the object is not moving, hence the frictional force is the static friction denoted by Fs, and in these two cases the object is moving and hence the frictional force is the kinetic friction denoted by Fk. We can plot the variation of frictional force with time as follows. We take time on the horizontal axis and frictional force in the vertical axis, and this is the variation of frictional force with time. When we are not applying any force to move the object, the frictional force is also zero. As we increase the applied force, frictional force also increases until it reaches a maximum value Fs. This maximum value is the maximum value of the static friction. Any further increase in the applied force results in the breaking of friction. The frictional force then reduces slightly and becomes almost constant, which is equal to the kinetic friction Fk. Microscopically, what is happening is that At a microscopic level, two surfaces are never flat. They are more like series of peaks and valleys. When two surfaces are placed together, only the peaks can come in contact. Only the peaks come in contact. The microscopic area of contact is very much less in comparison to the macroscopic area. These high points of contact fuse together, resulting in static friction. These high points of contact, these high points of contact fuse together, resulting in static friction when an attempt is made to slide surfaces relative to each other. At a threshold value, these fusion breaks, and thereafter this fusion continuously forms and breaks. Now, if the two surfaces are pressed harder, large force is required to break the fusion. Therefore, static friction is a force that resists the motion of an object related to another object when an attempt is made to move it. It is a type of friction that exists between two surfaces in contact and prevents one object from sliding or moving with respect to another object. The static friction force is less than or equal to the product of coefficient of static friction and the normal force. Similarly, kinetic friction is the force that opposes the motion of an object relative to another object when there is a relative motion between the two objects. It acts against the direction of motion of the object and is proportional to the normal force between the two objects and the coefficient of kinetic friction. Therefore, the kinetic frictional force is equal to the product of coefficient of kinetic friction and normal force. The coefficient of frictions for static and kinetic forces are dependent on this type of surfaces that are in contact. So now we will take an example. We have a rough surface and a block of mass m is kept on this surface. It is connected to another block of mass mb through a cord which wraps over a pulley. This pulley is massless and frictionless. The mass of these blocks are 2 kgs and 3 kgs. The coefficient of kinetic friction between block A and the rough surface is 0.2. Now, under the action of gravity, this block B accelerates in the vertical direction and it also pulls block A. Therefore, block A accelerates in the horizontal direction. The magnitude of both acceleration of both these blocks are the same. So in this problem, we will find the acceleration of these blocks. The forces that are acting on block B are the gravitational force, the tension from the cord. Similarly, the forces acting on block A are the tension from the cord, the gravitational force and the normal force, and the frictional force which opposes the motion in the horizontal direction. So for block A, we have these forces, the gravitational force in the downward direction, the normal force in the upward direction, tension force in the horizontal direction, and frictional force in the negative x direction. And this block A accelerates in the positive x direction. Therefore, for block A in y direction, we have two forces, normal force and gravitational force, and there is no acceleration in y direction. Therefore, the net force Fn minus mag is equal to 0 for block A. And this implies that the normal force is ma times g. Putting the values of ma and g, we can find the normal force as 3 into 9.8 equal to 19.6. Now, frictional force is equal to the coefficient of kinetic friction times the normal force. Therefore, the frictional force is obtained as mu k into Fn, Mu k is 0.2, Fn is 19.6, therefore the frictional force is 3.9 newtons. Similarly, in x direction, we have two forces, tension T and the frictional force, and there is acceleration in the x direction, positive x direction. Therefore, in x direction, net force T minus Fk is equal to ma times the acceleration, or we can rewrite it as T equals to ma times a plus Fk. Similarly, for block B, we have two forces in y direction, the gravitational force and the tension from the cord, and this block accelerates in the negative y direction. Therefore, the net force for block B, T minus mb times g, is equal to mass of block times acceleration, that is T minus mb times g is equal to minus of mb times a. This minus sign is there because the acceleration is in the negative y direction. We can read as mb times g minus t equals to mb times a. Now from this equation, we can take the value of t and put it here. So we'll take the value of t and put it here to obtain mb times g minus ma times a minus f equal to mb times a. From this we can find the value of a as mb times g minus fk divided by ma plus mb. Putting the values of ma, mb and g and fk, we get acceleration as 3 into 9.8 minus 3.9 divided by 3 plus 2, which is equal to 5.1 meters per second square. So the magnitude of acceleration of both these blocks are 5.1 meter per second square. Now we can find the value of the tension T in the cord from this equation. From this equation we can find the value of T as follows. T is equal to ma, which is equal to 2 times a, which we have found as 5.1, plus fk, which is 3.9. Therefore T is equal to 2 into 5.1 plus 3.9 equals to 14.1 newtons. Therefore the tension in the cord is equal to 14.1 newtons. So in the second example, we have an inclined surface with an angle of inclination of 30 degrees. A block of mass 10 kg is kept on this surface. The coefficient of kinetic friction between this block and this inclined surface is 0.3. Now gravity acts on this block. There is a component of gravity which is parallel to the inclined surface. So this block might try to slide down along the inclined surface. It may slide down or it might not slide down. So if it slides down, it will slide with an acceleration value of a. So in this problem, we are going to find whether this block slides, and if it slides, what will be the value of acceleration a. So the forces that are acting on this block are gravitational force in the vertically downward direction, the normal force in the direction which is perpendicular to the inclined surface, frictional force which is parallel to the inclined surface. Again, we will take component of gravitational force in two directions, one which is perpendicular to the inclined surface and another which is parallel to the inclined surface. So the component of gravitational force in the direction which is perpendicular to the inclined surface is mg cos 30, as this angle is 30 degrees. The component of force which is parallel to the inclined surface is mg sin 30. So for direction which is perpendicular to the inclined surface, we have two forces, Fn and mg cos 30, and there is no acceleration in this direction. Therefore the net force Fn minus mg cos 30 is equal to mass times zero acceleration. This means that normal force is mg cos 30. Putting the values of m and g, we obtain Fn as 10 into 9.8 into cos 30. This is equal to 84.8. newtons. So now we can obtain the value of frictional force by multiplying normal force with the coefficient of magnetic friction. Therefore, the frictional force is Fk equal to mu k times Fn is equal to 0.3 into 84.87, and this comes out to be 25.46 newtons. Now we will take forces in direction which is parallel to the inclined surface. So for direction which is parallel to the inclined surface, we have two forces, mg sin 30 and Fk. We'll first calculate the value of mg sin 30. So mg sin 30 is 10 into 9.8 into sin 30. This comes out to be 49 newtons. So as we can see, the force, this component of gravitational force is greater than the frictional force. This force is greater than the frictional force, and hence there is a net force in the direction parallel to the inclined surface, and therefore this block will slide down the inclined surface. Had this component of gravitational force less than the frictional force, this block would not have slided down. This block would not slide down. The conditions under which the component of gravitational force may be larger than the frictional force is the smaller angle of inclination or larger coefficient of friction. So in this case, this block will slide down the inclined surface with an acceleration A. So now, taking the net force in this direction and equating it to mass times acceleration, we obtain mg sin 30 minus F equals to ma. From this we obtain A as mg sin 30 minus Fk divided by m. Now we can put the value of mg sin 30, Fk and m to obtain A as 49 minus 25.46 divided by 10, and this comes out to be 2.35 meters per second square. So this block slides down the inclined surface with the acceleration whose value is 2.35 meters per second square.
That's all for this video. In the next video, we will learn about drag force and terminal velocity. If you like our videos, please press the like button and subscribe to our channel.